in space.
Welcome, everyone, to episode 125. I appreciate you taking the time to join me. As always, I am Alex Giorfanos, an aerospace engineer and science communicator, and we will be talking about space, the final frontier, our lifelong mission to dive deeper into space science, space fiction, and the near space future, to learn more and blow our minds like never before. This episode is jam-packed with science, but it's also going to cover a whole gamut of ideas and topics that are woven into the episode's story. Today in space, we're talking about the fundamentals of this thing we call science. Specifically, we'll be talking about hypothesis, theory, and law in science. I want to discuss what each of these actually are, and as well as something that rarely comes up. How does an idea climb the scientific ladder from hypothesis to theory and eventually a scientific law? But we won't stop there. Given that the Great American Eclipse happened on August 21st, 2017, we'll take some time to go over why this event is so awesome and what to look out for if you have the chance to view one in the future, which for the US is 2024. And also make sure to check out our Facebook Live What's Up segment from the morning of the eclipse to learn more about the total solar eclipses. This is also a great opportunity to talk about the journey of Einstein's theory of general relativity and how it went up the scientific ladder to become the leading scientific theory that replaced Newton's laws, which at that time were the leading scientific ideas of what is. Einstein's theory of general relativity has revolutionized how we understand how space and time function, as well as how they're related. We'll talk about how the total solar eclipse was the key to proving out Einstein's theory, and how even in the midst of World War I, he managed to keep driving himself forward, working on this, despite the ever-changing and violent world he found himself in. And we'll end the episode with my recordings from the day of the Great American Eclipse and go over what I learned from the experiments I tried that day. I was only in partial eclipse, but there's still a lot to learn from that. For those of you just listening, don't forget we're also a video podcast. You can find us on YouTube on our channel Today in Space. If you have any issues finding us, you can find all the video links for each episode over at todayinspace.net/home. Please give us a watch, a thumbs up, and subscribe. So, what is science? It's an ever-evolving framework of ideas that has been created to explain how the universe and the world around us work. Ideas are experimented, data is taken, and then those claims are tested in the coliseum of scientific peer review. You see, it's not just good enough to have an idea, create a test, and find your results. If you want your hypothesis to become a part of the giant scientific framework, you need to allow that idea to be tested by others, especially those who think you're wrong. To begin, let's start with the first rung of the scientific ladder. It is the first step in the scientific method. We are talking about, of course, the hypothesis. It's the very start, where scientists begin to attempt understanding the world in front of them. According to Britannica.com, the formulation and testing of a hypothesis is part of the scientific method, the approach scientists use when attempting to understand and test ideas about natural phenomena. The generation of a hypothesis is frequently described as a creative process and is based on existing scientific knowledge, intuition, or experience. Now, how does one create a hypothesis? Everyone is capable of creating a credible hypothesis, regardless of how many astrophysics courses or books they've read before. In fact, some of the greatest hypotheses have come from a daydream or a burst of thought and inspiration. The major difference between an idea and a hypothesis is action. That action comes in the form of a test to see whether or not your idea holds water. In academia and research, creating a hypothesis is a little more complex. A literature review probably needs to be conducted before you can create a hypothesis. Now, before your anxiety goes through the roof, a literature review is not like an IRS audit or even a test. All it means is that you need to do your homework. It involves researching your subject area and finding out what other people have found on the subject. From there, you create your hypothesis and find a test to get data and analyze if your hypothesis is right or wrong. So, in the simplest of terms, a hypothesis is an educated guess of how things in reality work. From there, you follow the scientific method on your way up the scientific ladder of ideas. Create a test for your hypothesis, analyze your data, draw conclusions, and then If all worked out, you can share your idea with the world. If not, you go back to the drawing board and either redo the test, change the test, or, if needed, change the hypothesis. Now, before we move on, I do have some important notes to add. Number one, the test you create must be reproducible so that the experiment can be conducted again and again and again. This is really important because then others can try and see if you're wrong or if you're right. And number two, empirical data is king. Facts don't care about your feelings. It takes courage to challenge old thought or create new one. And so for your own sake, make sure you can gather unbiased data so that you know that your experiment really worked. Don't cheat yourself out of success by smudging or getting bad data. It's not worth it. The next rung of the scientific ladder is a theory. This is arguably the most used term of the three, and a big reason why I did this episode in the first place. Somehow, the term theory as used in science is also used in the mainstream, but to discuss someone's strongly held idea. And that's not what a scientific theory is. And I would guess that most people's theories have never gone through the cheese grater of truth that is the scientific peer review process. I also don't think most people have ever had their ideas challenged, but we're getting sidetracked. So, according to Merriam-Webster.com, a scientific theory is a plausible or scientifically acceptable general principle or body of principles offered to explain phenomena, not to be confused with the general use of the word theory, defined as an ideal or hypothetical set of facts, principles, or circumstances often used in the phrase in theory. You ever heard that one? Essentially, the difference between just a theory and a scientific theory is as follows. A scientific theory uses mathematics and science to explain a general framework of how something in reality works. A non-scientific theory can be simply a hypothesis, but without testing done on the theorizer's part. And there are various kinds of scientific theories, from newly tested to thoroughly tested, and then everywhere in between. Scientific theories are frameworks, tools, and equations you can use to discern reality. The more a theory is tested and passed through the peer review process, the better that theory becomes. Which brings up a very important point. Not all scientific theories are equal in their metaphorical weight of knowledge and correctness. Now, a good way to think of it is each scientific theory is an opinion, and the amount of times it has been tested and proved out or used to create another working theory gives it a certain amount of metaphorical weight. This means we can have theories with little to no ability to test, like string theory, which are fun, but they weigh very light on the scientific significance scale, where the theory of general relativity has been tested many times and has been used to create entire fields of science, including string theory, and weighs heavy on the scientific scale of theories. Now, in my opinion, this point seems to be missed by a lot of people, including the scientists and the science deniers. Science deniers will compare science theories like evolution and say, well, it's just a theory, which, as we discussed before, is the wrong scientific definition for it. It's also a different term. On the other hand, many science-minded folks will get emotional about someone denying science. They'll attempt to defend science or go farther than a scientific theory has intellectual legs to travel, claiming that it's a law, or that the one I hear most often is that there's no denying a theory like evolution. And this bothers me because it's not intellectually honest, and it's just an attempt to dig your heels into the ground and defend something you care about. Admirable, yes, but not productive or helpful. So, the best thing for science is to explain what we know and be specific about the things we don't know. Actually defining what a theory is would help. Lying about this or overreaching will give deniers a reason to claim it's all bullshit, thus muddying the waters of honest intellectual discussion. Let the facts be facts, and let the brutally honest peer review process handle the tough work. All we have to do as communicating scientists, or just people passionate about science, which I think you are, is to share this new knowledge with others. My last thought on scientific theories. In my opinion, even a metaphorically science-heavy theory is not a perfect explanation of how the universe works. This seems to go over a lot of people's heads when things like evolution get brought up. Anyone who's gone through the gauntlet of a STEM education will know that Even great theories don't explain everything when you apply it to the real world. That's why tests are still hard in school. Like, it's not a plug and play with numbers. It would be great, but it's not. Science only really gives us a way to describe, predict, and sometimes manipulate the world around us based on the limits of our physical universe. There is a tendency, however, to think that scientists know everything or that we have all the answers. I'm here to tell you that's not true. In fact, scientists spend most of their time working and learning on new things, which never ends. Science is a tool that gives us a reproducible and accountable explanation for how things work, which seems to be mistaken with us knowing everything. The double-edged sword of science is that even when you've found a theory that encompasses how reality works, you open up the box of more questions that need answering. It's like cutting off the head of the Hydra and two more take its place. This is a great thing if you're looking to spend your career searching for answers and learning about the universe. You'll have more to do than you'll ever fit into a lifetime, but if you're looking for the answer or a simple yes or no answer to life, science can't do that for you. The final rung of the scientific ladder is reserved for scientific law. Scientific laws are very similar to theories in science. They help us understand our physical reality in the universe and provide the boiled down, simplified, and distilled expression of what is. But there is a major difference. Scientific theories provide a framework of equations or an explanation for a phenomenon. Scientific laws explain in the simplest of terms what has been discovered after testing and observing the same thing over and over and over again. Simply put, scientific laws attempt to describe the fundamental nature of the universe. There's a catch, though. Scientific laws are observed over and over again as long as the conditions for the observation and phenomena stay the same. If the conditions are not the same, or if they change slightly, you may not get the same results. Just as in life, there isn't one answer to rule them all. Instead, we have general rules, in this case scientific laws, that work all of the time, unless something changes. Some examples. Newton's law of gravity only applied for weak gravitational fields and did not help explain how the universe works, or really even explain what gravity was. Aerodynamics, love it. Bernoulli's principle is scientific law for all incompressible flow, things like air and water under normal conditions and speeds. But as soon as the flow changes, like breaking the sound barrier, for instance, going really fast, Bernoulli's principle fails because we are now dealing with fluids that are being compressed and thus dynamically changing how these gases flow and react, requiring a new set of rules to explain this compressible flow phenomena. In order for something to become scientific law, it must be tested for a very, very, very long time. Long enough that enough people have done the test so many times that it's seen as a literal expression of what is, because it has been seen to do this virtually every time. For instance, water is liquid if it's experiencing 1 atmosphere of pressure and its temperature is between 0 and 100 degrees Celsius. If the pressure changes or the temperature is out of that range, water is no longer liquid. But it can also be liquid under different conditions. Basically, science is great, but life and the universe is complicated. Scientific theories and laws make it a bit easier to understand. And now let's do a little space story time. The Great American Eclipse of 2017 was a great excuse to discuss total solar eclipses, as if I needed one. One of the greatest examples of the scientific use of a total solar eclipse is the story of Einstein's theory of general relativity. It's my favorite example of how an idea climbs the scientific ladder. Albert Einstein's history is very interesting, and I love watching documentaries and reading about his life. I would love to talk more about both Einstein and his thoughts, but that's for another episode. On this episode, I want to talk about how his scientific idea went from a daydream at work to becoming the leading scientific law, replacing Newton's. But I do want to touch on how Einstein the individual was able to pursue his idea up the scientific ladder and what he went through to do so. Before we start, let's get this up here. So this is a bust of Albert Einstein that I 3D printed using the Prusa i3 Mark II 3D printer. It was originally created by LS Miniatures and is available for free to download on thingiverse.com. The detail that came out of this is just simply amazing, and it's probably the most detailed thing I've 3D printed so far. I'll have a video on AG3D soon detailing how I made this awesome model later. But in the meantime, I'll put Einstein up here, and let's begin. The hypothesis for one of Albert Einstein's most important theories began from a simple daydream he had one day while working as a patent clerk in Switzerland in the spring of 1905. Einstein was riding on the bus in Bern and looked back at the clock tower as they drove away. He wondered what would happen if the bus were moving away from the clock tower at almost the speed of light. What would happen to time if you looked back at the clock tower? In his imagination, Einstein saw that the clock tower was frozen in time as the bus approached the speed of light, moving away from the clock tower. Einstein described the sensation as if a storm broke inside my mind. All of a sudden, everything just kept gushing forward. Now, the mind storm of Einstein happened because everything he knew about science at that time started to put all the pieces together. If you're moving through space at the speed of light, that's as fast as you can go. That means the light coming off of something like a clock tower won't be able to reach you since you're already going as fast as possible, which also meant the closer you're moving to the speed of light, the slower you are going through time. This was the beginning of Einstein's theory of special relativity, which says that space and time are connected and deeply intertwined. So much so, they're one and the same and part of this flexible, dimensional fabric called space-time. All of this came from an idea Einstein had on the bus one day. Before Einstein's hypothesis, the general scientific consensus was that space was this place where celestial bodies moved in predictable and clock-like motion. Pretty boring. But with the idea of space-time, the idea of how the universe grew and expanded and evolved over time and will evolve over time, made it something exciting, dynamic, and with just infinite possibilities. So Einstein, the patent clerk, began his journey up the scientific ladder with the creation of a hypothesis that space and time are interconnected. In order to propose this idea as a theory, Einstein wrote the special relativity paper with the help of his wife Mileva, who was also a physicist. The paper outlined the mathematics behind the theory and attempted to show what happened to space and time at the speed of light. The special relativity paper was published in June of 1905 in volume 17 of the Annalen der Physik, which I apologize if I'm mispronouncing that, but it's also one of the oldest scientific journals on physics and was first published in 1799. This paper brought Einstein's idea up the scientific ladder from hypothesis to theory. He took his original idea and with the help of his wife Mileva created the framework for how this phenomena works, based on what he already knew about the universe. But once the paper was published, instead of any kind of criticism, he heard nothing. Silence. Some of this was because no one knew who Einstein was. Part of it was also because not many people, even scientists at the time, knew what he was talking about. That's how crazy and revolutionary this idea was. 2 years later, Einstein reviewed his theory and realized it was fundamentally limited. Special relativity was only able to describe what it was like for an object moving at a constant speed of light. In real life and in the universe, everything is accelerating always. Speeding up, speeding down, when you're driving, bumps in the road, friction, all of those things and more make constant speed almost impossible to maintain and keep up. So Einstein adjusted his theory to adapt to the real world. And in my opinion, this is a really important part of the process. It's intellectually honest and scientific to change your mind when you're given new facts and information. And we've talked about this a few episodes ago in the podcast. Einstein made the decision to make this theory even more incredible and revolutionary so that it could account for the whole universe. This new equation of relativity would generalize everything in the universe. Einstein realized that there was also another missing element in his original theory: gravity. Now, let's take a quick trip back in time to the 1600s, to Isaac Newton. Now, Newton had been the first to really figure out that gravity existed. He described it as a force that pulled objects as it fell, and it was also invisible. And if you remember Newton's laws, the first states that an object in motion or at rest will stay in that state unless a force is acted upon it to change its state of motion. So gravitational pull makes a lot of sense if you look at it through Isaac Newton's thought process. Now, if I hold this at rest and then drop it, what caused the object to fall? Well, my hand didn't push it down, I just let it go. So some force must be pulling it down, Newton thought. Sorry, Einstein. So he created the idea and the framework for gravitational pull, which was this magical force that acted on objects, causing them to fall. But even Newton thought that there was more to this. But he had to reluctantly leave the mysterious gravity problem for someone else and published his laws of motion in 1687. Now, in my opinion, it's a pretty interesting thing that we could create a scientific law and a new force without understanding how it worked. Even scientific theories and laws that express how the world around us works can be built on things we can't see or fully understand. And to me, it's an example of how powerful observation and the scientific method is. Even though Newton didn't understand the secret of this invisible force called gravity, he could still observe and construct a framework to explain the world around him. And more importantly, it shows that you don't have to be perfect or understand everything to create an idea that ultimately changes how we view the world and the universe. Now, moving forward in time to the 1900s, back to Einstein. One day, while staring out his window at work, Einstein imagined what would happen if a worker on the roof fell to the ground. First, the worker would become weightless in freefall. Even if the worker were in an elevator that had just been cut, both would fall and become weightless. This is where Einstein started piecing together the puzzle of gravity and the riddle that Newton had left behind over 200 years ago. Einstein realized that gravity was not the invisible force acting on everything that Newton had originally thought. Gravity wasn't the thing that was pulling on the falling object. It was space that was actually pushing the worker and the free-falling elevator towards the surface of the Earth. Space is not flat and rigid. It can be curved and manipulated. Space pushes you and I and all things pushable. Einstein figured out that how much space is pushing something is determined by the influence of massive objects like the sun or the moon or Earth, resulting in gravity. Even further, Einstein realized that space and time are a fluid, dynamic thing that is much more complex and beautiful than we could have ever imagined. Now, this new thought brings Einstein to create his theory of general relativity. Now, Einstein might be able to propose a general equation for how the universe works. The math itself takes him years to solve and proof out. The sheer visualization of what he's talking about is almost impossible to imagine, even for Einstein. It takes years of thinking and writing and rewriting equations to create the test for this theory. While he works on the math behind his new theory, Einstein becomes Professor Einstein in Zurich in 1911 and starts gaining recognition for his other work amongst the scientific community. 4 years go by as he works to put together the framework for his theory of general relativity. In order for his theory to be recognized and accepted, he needed to create a test for it. The basic idea behind this test is as follows. If space can be manipulated, then a beam of light could be influenced as it passes by something massive enough to bend the beam of light. Einstein would also have to find out exactly how much that beam of light would bend. But where can you test something as crazy as this? I mean, what lab could you use to conduct this experiment? Space, of course! The most massive thing we have near us is the sun. And others have been measuring the position of the stars for years. So if the sun closely passes a distant star, and the position of the light from the star changes by the amount he predicts, then Einstein's theory can be tested and potentially proven. Once Einstein laid out the specific procedure for the test, he reached out to astronomers and astrophysicists. Why? Because the perfect time to view stars that close enough to bend the light around the sun is during a total solar eclipse. And at that time, no one was better equipped than astronomers and astrophysicists. The actual scientific battleground for the theory of general relativity was within the path of totality from a total solar eclipse. Astronomers used telescopes to record star plates and document the position of everything. The star would need to pass close enough by the sun for the light to bend around it. But under normal conditions, that star wouldn't be seen because of how bright the sun is. If someone could record the position of a distant known star that close to the sun during a total solar eclipse, then Einstein could finally see if he was correct. In April of 1914, Einstein joins the most prestigious scientific institute in Berlin after being personally requested. Using his new position, he released his prediction to the public, asking astronomers to observe this. But even Einstein's new position didn't get astronomers to help him. They were busy with their own work, and they didn't respond. But a young German astronomer, Erwin Finley Freundlich, as well as an American astronomer, William Campbell, did take the call. They set up to record the stars during the total solar eclipse on August 21st, 1914. The path of totality would pass through Crimea in Russian territory. But on June 28th, 1914, Archduke Franz Ferdinand of Austria gets assassinated, and the whole world plunges into World War I. While the two astronomer parties were preparing for the eclipse, Russian soldiers approached. The Freundlich party was arrested for being suspected of being spies, and all the equipment gets confiscated, and they spend months as Russian prisoners of war. The Campbell party was allowed to conduct the experiment since the U.S. was neutral, but the clouds never opened up, and the chance to test Einstein's theory passes away. In hindsight, it was actually good that his observations failed, because Einstein had the math wrong, although he didn't know it at the time. The results would have shown half the deflected angle of the bending light around the sun, and it would have disproven Einstein if they had the chance to capture the stars during the eclipse. It would have ruined Einstein, and at the time, Einstein thought it was all over. Meanwhile, the world plunged further into chaos. Patriotism grew to outrageous lengths, and everyone around him became obsessed with the war. Even his closest friend at the Institute, Fritz Haber, used his brilliance to create poison gas. The same science Haber had used to revolutionize fertilizer to feed millions, he would be using to kill thousands in just the first test of the battlefield. Einstein, a pacifist, had no place in the world he lived anymore. He was alone. After failing to convince the academics that war was not the only option, he retreated to his small apartment to continue his work. After 3 years of asking astronomers to capture the stars during a total solar eclipse, he finally realizes his math was wrong. He tried to visualize how space and time were connected and where he got his math wrong. Equation after equation, mistake after mistake, Einstein pushed forward and essentially trying to make all the mistakes he could until eventually he came across the answer. It's now 1915, 10 years after he started work on his theory. He's obsessed with completing his work and finding the mathematical solution to his theory. At the same time, he got invited to present his theory at the Prussian Academy in front of the leading scientific minds at the time. Something he always wanted, but he wasn't ready. While making headway on his mathematics, he took a different speaking gig to prepare for the Prussian Academy. And sitting in the audience was arguably the greatest mathematician of all time, David Hilbert. And Hilbert saw that Einstein was onto something and decided to try and finish the math before Einstein did, and essentially take credit for Einstein's theory. But Einstein didn't back down and continued to work to complete the math of his theory. He found the answer to his problem in the orbit of Mercury. Newton's description of celestial motion contradicted the actual path of Mercury's orbit, but in reality, Mercury's orbit represented a flower petal due to the tilt in its orbit. This was only a riddle because we had a limited idea of what gravity really was. Einstein used his theory of general relativity to painfully calculate the position of Mercury as it orbited the sun. When he finished his calculations, he realized his theory was correct in describing the motion of how celestial bodies orbit the sun, and was so overwhelmed that he actually had heart palpitations and couldn't even focus on his work. With his math correct, he presented to the Prussian Academy, and the whole scientific world went crazy. Everything we knew up until this point could be wrong, and this Albert Einstein, a Jewish German scientist in the middle of World War I, could be right. But the only way to find out was from capturing an eclipse. At this point, word spread about Einstein's theory of general relativity and started to gain traction. So much so, it actually made its way across the battlefields of the Great War, which was really something since, until now, Einstein's work had been contained within the German-speaking science community. Dutch physicist William de Sitter of Holland, which was a neutral nation during World War I, translated and sent a copy of Einstein's work to British astronomer Arthur Eddington. Eddington decided to set up an expedition to capture the total solar eclipse. Around the same time, American astronomer Campbell got back in the game and created a custom telescope just for the eclipse. Campbell was the first to capture the eclipse, but didn't see what Einstein had predicted. After Eddington managed to capture the eclipse and was working on the position of the stars, Campbell was presenting his results to the scientific world. This is a big moment in the battleground of science. Being the one who proves or disproves a theory is a big deal. And if you make a mistake trying to prove a theory wrong, it could be the end of your career. Before Campbell revealed his results, a message from Eddington came in stating that it's possible Einstein's right. Smartly, Campbell decided to wait until Eddington presented his results. And once Eddington revealed that the star's position was off by what Einstein predicted, the world went crazy. The war-stricken world fell in love with the pacifist German Jewish theoretical physicist Albert Einstein. He became extremely famous, and with that fame brought lots of doubt about his theory in the scientific community. But the cheese grater of truth that is the peer review process, as well as more viewings of the total solar eclipses, vindicated Einstein, and our whole understanding of how the universe worked changed. With all this testing, Einstein's theory became natural scientific law because it was observed to happen again and again and again. But it also opened up new questions. Whole new branches of science were created. Inspired people everywhere started to learn about the warping of space-time and how the universe works. This set up the groundwork for the future for NASA and the space race to the moon, and of course, the existence of today in space. And that is the story of how Einstein's dream on a bus while working as a patent clerk made its way up the scientific ladder to become a theory. And after World War and the brutal peer review process, it became natural scientific law. I hope you enjoyed this session of Space Story Time and my favorite example of how scientific idea can make its way up the ladder. And also how determination and persistence can help you achieve anything, even if the world around you seems on the edge of annihilation. Now, I'd like to share the experiments I conducted during the Great American Eclipse of 2017 from my own backyard. I wasn't able to go to the path of totality, but I was able to view the partial solar eclipse. I attempted a few experiments, not all of which worked, but I did learn a lot from my very first eclipse. So, let's begin. Hello, everybody. Welcome to Today in Space. I am, this is a crazy day. I just took a few looks with my solar glasses, and it's, knowing what's happening, it's just like, oh my god, this is actually happening right now. And to actually see it is just so cool. So we've got all our stuff. We've got our experiments set up. I'm actually using a selfie stick for the first time, but this is how we get it done and make it look good. So over here, we're doing the test with the shade, so we can actually test what the shade is like throughout this eclipse phase. We can actually see how it's changing and all that stuff. So it's already started, but maximum's at 246. I think it's 150 right now. So I'm just sitting here working on this stuff, getting things ready, acclimating to the one where it is a hot day, but I gotta wear my gear. I gotta support, and this is just an amazing friggin' day, and I'm very excited to have you guys joining me so we can actually enjoy this. So I'm gonna also record sounds of the wildlife in the area, which you can actually hear. I don't know if you hear it very well. But we're going to take it with this higher def microphone, have the mic gain almost all the way up, so you can pick up all the sounds and see what happens at maximum coverage. We're only 71%. I saw 68% online earlier. I'm going by what my actual NASA model says here, which is between 70 and 72%. So we're going to go with that and see what happens. And I'm going to figure out this selfie stick a little bit better. So, awesome stuff. Go science. Check in soon. So, it's a little after 2 p.m. Eastern Standard Time, and the sun just came out in force. Almost no clouds at the moment. And I've got the pinhole projector, and I just wanted to show you what it actually looks like, what I'm actually looking at from here. If you've never done one before. So, let's check it out. Like I said, you line up the back hole with here, and then you just line yourself up, and see that? There is the moon going in front of the sun. I was just taking a look at the eclipse right now with the glasses. I mean, I'm speechless because of because of the gravity of what's happening. It's it's really insane, and I can't even imagine what it was like back in the day when some dude was like, "Hey, guess what? the moon is gonna come in front of the sun, and like talk all this crazy shit, and you're just a peasant sitting there like, okay, dude. Or even like a king, right? And some warlock comes in and tries to tell you all these things, like, and then it happens. I mean, that's some pretty powerful shit back in the day, like, and to be able to view it with these glasses, like, it's pretty. I get that. Do you ever get the feeling when you're looking at the stars, or when you're thinking about outer space, where you feel like almost your feet leave from under you because you like put yourself there? Whew. Man, that's every time I look at the eclipse, that's exactly how I feel, and it's just insane. So I'm gonna take a few more looks here and freak myself out a little bit more. Yeah, all I can think about is the Apollo missions when they went to the moon, and just how far away it was, how difficult it was with everything that was going on with Apollo 13. After 2 missions earlier, they had just changed the world by touching the surface of the moon for the first time in human existence. I mean, it's pretty crazy, and it's right there, and just like real life, other things influence you. Your environment influences you, and I am definitely being influenced by my environment right now. So this is pretty crazy. So it is around 2:20-ish. Let's take a look. It's this little sliver now. It's kind of crazy. Try and get it back. The clouds are not helping. In typical New England fashion, it is it is not perfect condition, but we're getting something. Oh, there's a better view. Yeah, it's perfect. Look at that. Just when I needed it. Thank you, universe. So yeah, pretty insane with just a really simple project that costs you almost nothing can help you do. Go science. It definitely seems like the total solar eclipse is really the big thing, but we won't know until we look back, because I was actually in the middle of all this, so I can't tell if the light really changed a lot. I've already adjusted to it because there was no stark shut off, so I won't know that, and the sounds sound relatively all the same. So, pretty cool day though. We're going to try the pinhole projector one more time. I think what happened with this was you're actually supposed to print a bunch of different sizes and test them out and see which one works best. But it was a cool, fun project, and it looked really, really cool. So not bad for last minute, and I'm very excited to see what this test with the shadows did, what we can pick up from that, because if we can pick up any kind of difference from the beginning to the end, that would just be really cool. Otherwise, it was a good day of just doing science, sweating a little bit, and getting outside. I definitely lied in my last video. I was getting a little anxious and overestimated the time. So I went back to that original time, the 2:47. I double checked it. That's actually the time. And I'm glad I did, because everything has changed a little bit. It's a subtle change, but it's a little bit quieter. The air is definitely cooler. I can feel, literally feel that it's less warm. It was really hot out here. I was sweating, and now I can tell the heat is less. So jump the gun on the earlier prediction, but still really, really freaking cool. So what I'm going to do is check the pinhole camera now that we get some clear sky, so you guys can actually see what it looks like at our totality, which is 71% coverage. So let's check it out. I'd say of all my equipment today, the pinhole projector that I made last year has definitely been performing the best. It's just friggin' amazing. This is just such a cool thing, and the thing that's really getting me is like the visible response. I think we must have like just gone by it. It's such a strange feeling when everything gets like just comes back all of a sudden. Like it was really silent there for about the 2 to 3 minutes that it was supposed to be. That was strange, but this is so crazy. This has been a a weird day to say the least. A weird, awesome science day. It's definitely strange sitting out here and now feeling it get warmer after it was colder. It's I can't even imagine all the stimuli people must have been going through in the actual total solar eclipse, the actual totality line. This is the record of it. Like it was weird. There's no other way to really describe it. Yeah, I've been like scratching my head. I've kind of been speechless. Like I don't really know what to say yet. Just gonna wait here, and I'm gonna feel the air temperature get warmer and get hotter, and I'm gonna start sweating again. I'm gonna pull my thoughts together, and we'll bring it all back, and I'll give you guys a recap. A weird thing I did notice was near the maximum, like 10 minutes before and after, there was a visible difference in like the glare that was coming from the sun. You know, there's always a glare where you're just like, oh, okay, that's the sun. I know not to look there. But it was a little bit different. It actually, I guess the word to use is softer, but that's not really a scientific term. But it was cooler. So I'm not saying it made me want to look at the sun a little bit more, but it was definitely interesting. Our pinhole projector fun. So let's check this out. This is a little after the maximum for the eclipse here. There it is. Hey guys, so back here in the shade after the solar eclipse here, and I was trying to figure out what I was feeling. I couldn't put it together. I just didn't know, was it freaking out? Was it excitement? Was it all those things? But I was super, super excited, and obviously, you know, a little nervous, putting the show together, making sure things are going right. But when I was watching it through the glasses, it was humbling at the same time. So I had all this pent-up energy inside about, you know, making sure this is going to go right and all that stuff, mixed with the awesomeness of what I was seeing. So that's a weird feeling to be all kind of bundled up with energy and then just kind of getting slapped around with humbleness. It was really cool. So I am going to enjoy the rest of my day, put together that video, and we'll talk soon, guys. Let's close out this episode with what I learned from my first partial solar eclipse viewing. Number one, I learned once again that multitasking can go too far. It turns out recording, directing, hosting, and conducting 4 experiments simultaneously means you might not get the best results. I was excited, what can I say? It was the first time as a scientifically able adult that I experienced a solar eclipse. I just felt the need to try and do as much science as I possibly could. Number 2, some of the experiments, like the video recording of the shadows changing and the pinhole projector I 3D printed from NASA, were experiments I should have taken the time to practice before the eclipse. You only have 2 to 2.5 minutes anyways. Trying to troubleshoot problems or simply running the experiment for the first time during the eclipse is not ideal. What I recommend to you is to practice any experiment you want to try a few days before the event. Try what you'll be doing so you prepare and can do your best. Oh, and going over the instructions a few times beforehand helps too. I say that because I literally didn't read the instructions for the NASA one. Number 3, the audio equipment was the only experiment I thought was a toss-up. I didn't expect to find anything. Although I was able to pick up the sounds of nature and the neighborhood, there isn't a good way for me to know that the sound actually got quieter. To be honest, I'm also not really sure what I'm listening for, or even what I think qualifies for nature being affected is logical. It's not my wheelhouse. If I did it again, though, I would think having an array of microphones across the yard in key spots would be better. The cardboard pinhole projector I made a little over a year ago was the clear winner here. Not only was it my best experiment to view the eclipse, it was also my most reliable piece of solar eclipse viewing hardware, and it's made of 4 things: cardboard, aluminum foil, Scotch tape, and a piece of paper. In the end, I did the best I could with my first partial solar eclipse, and I'm proud of that. I'm sure there are some other experiments I wasn't aware of, and if you know of any, please leave them in the comments below. I'd love to learn about them, and I'm sure a few other people would too. After reviewing everything and taking the time to think about that day, I realized that I was really overwhelmed. In a good way, like I was excited and not stressed. To be honest, I was nerding out. Every time I got a view of the moon in front of the sun, I felt this strange feeling, almost as if the floor came out from under me or I'm at the top of a roller coaster. Seeing the moon clearly obstructing the sun made it incredibly easy to gain perspective of our solar system and just how small I and every one of us are in the big picture. As if standing on the earth and feeling gravity was nothing compared to the gravity of the situation of just being in the solar system. I'm not talking about the universe. I'm talking about our little sandbox of a solar system inside the cosmic backyard called the Milky Way galaxy. And the universe is still the universe of that. It was strange to do science and have this deeply emotional connection to the event. That is weird when you're doing science. You always want to be like, oh man, this is science, this is awesome, but you usually only get that when you get results. What I'm trying to say is that science nerd emotions are strong with this one. I cannot wait to travel and see the total solar eclipse next in 2020. But it wasn't just me. It was a strangely emotional day for a lot of scientists that went to the path of totality. I remember reading a lot of articles and tweets from science people saying just that they didn't expect to be taken aback and emotionally triggered by the awesomeness of the total solar eclipse. And that brings me to my final piece of advice for anyone who wants to go to their very first total solar eclipse. Experience the eclipse with your human senses. Experience the sight, the sounds, and feel the temperature drop. Live in that moment and take it in. If you can't help yourself and you have to do an experiment, look, I get it. Pick one, practice it, and enjoy yourself. For this episode, I want to do something special, so make sure to check out the end of this episode for the credits and see all of the pictures from some of the amazing people I know that went to the path of totality in the 2017 Great American Eclipse. What they all managed to capture from that day is simply amazing. Some had telescopes, some were camped out in national parks along with the path, but all of them did a fantastic job, and I'm really excited for you to see them. And that does it for this episode of Today in Space. Thank you for joining me. I really do appreciate you taking the time. If you're interested in what else we do here at Today in Space, you can head over to our website at www.todayinspace.net, find us on YouTube on our page Today in Space, or listen to us on iTunes or your favorite podcast player. I am Alex Giorfano, science communicator, and until next time, spread love and spread science.